So when we came up with some arguments for the heliocentric theory earlier, that was in the context of different types of reasoning. So we were trying to illustrate deductive reasoning, inductive reasoning, abductive reasoning, and speculative deductive reasoning. And the argument for the heliocentric theory is speculative deductive. So it's an explanation-based argument. So I didn't go into the details of the heliocentric theory at that time. I simply used parts of it to give a flavor of what speculative deductive reasoning is. Now I want to approach it from a different perspective, namely, what does it take to provide a critical understanding of the heliocentric theory using speculative deductive reasoning? So I'm changing gears somewhat. And implicit in that changing of gears is the idea that if you're aiming at inquiry-oriented education, then there are certain things that ought to be included in the syllabus. And these include the following issues. One, how do we construct, defend, and evaluate theories, and the theories would include mathematical, scientific, and humanistic theories. So students should have an understanding of these processes, these activities. They should also be able to construct, defend, and evaluate these three types of theories. So both the understanding and the ability. And this is where, as part of this, is defending scientific theories, and that's where heliocentric theory comes in as an example. At that point, I wasn't particularly interested in the heliocentric theory itself, but in what it offered by way of illustrating speculative deduction. We should also consider how do we construct, defend, and evaluate not mathematical, scientific, and humanistic theories, but interpretations or explanations within well, at this point I wouldn't include mathematical, scientific, and humanistic theories. And this is where abductive reasoning comes in. If you want to defend these guys, and this is where speculative deductive reasoning comes in. Then you could ask other kinds of questions. How do we design experiments? How do we do all kinds of other things? I'm not, at this point, I'm assuming that there's a few more things here which I will not spell out. So the question that I want to address today has to do with this. And as part of this, we need to have an understanding of the evidence and arguments for the heliocentric theory and our students. So what exactly are the differences between these two? Even though it is called heliocentric, that is sun-centered and earth-centered, the crucial difference between them is that geocentric theory is built on the following propositions. Number one, the Earth is completely stationary. And in contrast, the heliocentric theory negates this. The heliocentric theory says no to this. The Earth is not stationary. And the details would be the Earth rotates and revolves around the sun. So the question is, why should we believe this as opposed to this? The second proposition in the geocentric theory is that the Earth is the center of the universe. Obviously, if the Earth is revolving around something else, again, this theory is saying, no, the Earth is not the center. At the point when the theory was constructed, for the solar system, the sun is the center. We leave out the universe here. Sun is the center of the solar system. And whether or not the solar system is the center, that's a separate question. We're not making any claims. Now this is probably the most important proposition, which when denied created a whole lot of problems for a conception of a worldview, because that comes from the idea that humans are God's special creation, and God created the earth specially for humans and put humans at the center of the universe. And now what happens here is that humans are displaced from the center. So there is this question, is it true that humans are God's special creatures? That's why it created a lot of emotional reaction. As far as this is concerned, Earth being stationary, that is common sense. We experience the Earth as being completely stationary. So if you believe in experiential learning, that's where we should begin. Children and all human beings, the first step would be to believe that the Earth doesn't move, Earth is not stationary, the Earth is completely stationary, and you want children to believe this instead. And the movement from here, commonsensical notion, to this is not easy. And by accepting children to believe what is counterintuitive on the basis of simply an assertion is extremely harmful to children's belief systems. So how do we move from here to here in a rational way is the question. So in the
Sriram has to
yeah, oh, sorry. Yeah.
In the heliocentric theory, we club this rotate and revolve, right, in the beginning as one. Should that be split into two? Because the opposite of X, Earth is stationary, is Earth revolving.
Yeah.
I don't care whether it is rotating.
Oh, okay, couple of other things. Here, we say the Earth, the Sun and other planets revolve around the Sun, around the Earth. Unlike this one. Because if Earth is the center of the universe, obviously the Sun and the other, Sun is a planet and the other planets also revolve. And the other is, there are a few other things here, such as stars. I will not go into the AP cycle and so on. And here on the other hand, the central propositions of the heliocentric theory is the Earth revolves around the Sun. And let's split it into two. The Earth rotates on an axis. And the third proposition is the axis of rotation is tilted to the plane of revolution. These are the three propositions that we need to defend. Of course, there are other things. So what is the trajectory of rotation, is that a revolution? Is that a circle or an ellipse? I'm going to ignore that, it doesn't really matter. I mean, it doesn't matter for purpose of school children. What exactly is the tilt of the, what is the angle of tilt? Doesn't matter. It's all that we need to know is slightly tilted. Whether it is 22 or 23 or 24, it doesn't really matter. Those are matters of detail. At the school level, this is irrelevant. Of course, for the examination purposes, they have to know the exact figure. But they are not going to figure out how you arrive at that number. It's way too complicated. So what we need to do is to defend these propositions. And when we defend these propositions, we have to see if these propositions will also explain the phenomena that we are trying to explain. So I've given a list of 10 observational generalizations that we need to explain in the handout that was given. So let's go through them one by one. In a classroom, I think you need to go through all the 10 to provide a meaningful defense of the heliocentric theory. Some of them are fairly easy, but they will not give you a defense, they'll simply give you competing explanations. So if you look at day and night, okay, if you look at day and night, notice that this is sufficient. There's a sun here and the earth rotates, you get the day and night effect. And on this side, the earth is fixed and the sun goes around the earth. That will give you exactly the same result. So as far as that is concerned, the first phenomenon can be explained in both ways. But notice the switch. Here the explanation is that the earth rotates, but here the explanation is that the sun revolves around the earth. Earth's revolution is not needed for day and night. Okay, the next thing is, in addition to the sun's day and night and also the associated differences in the position of the sun, apparent movement of the sun from east to west, we also have the apparent movement of the stars. So if you look at the night sky for a long time, you discover that the position of stars keep changing, and they appear to be moving in a circular fashion around the pole star. And the way to explain that is, again, the earth rotates. Okay, the earth rotates, and the axis of rotation is through the pole star. So if the earth rotates around the pole star will appear fixed, and the other stars will appear to be revolving around the pole star. And the explanation here is that the earth is stationary, and the whole globe on which the stars are stuck, the entire globe rotates. That will give you again the same explanation.
Or the dome rotates.
No.
What did I say?
Dome rotates.
You said globe.
Oh, sorry.
No.
Whenever I say
Globe.
globe, I mean the dome. Yes, thank you. Yeah. Okay, so it's important to begin from here, because at this point we have no argument to choose the heliocentric theory against the geocentric theory. So why should we believe that the earth is not stationary is the question. Okay. I'm not sure about which phenomenon to pick after this, but it's a good idea to pick the, after going through the daily cycle of the sun's daily movement and the star's daily movement, the sun's yearly movement. So if you look at the horizon, let's say this is the horizon and there are trees and there is a house here. If you look at the sunrise every day, you find sun rises here one day, the next year it rises here, next rises here. The position of the sun keeps moving in a south-north fashion, and the sun keeps to be traveling northwards, and then it At some point it stops there and reverses the direction and then it stops and goes back. So this one, for the sun to move in one direction and come back, it takes a little more than 365 days. So a year. To put it observationally, what we should say is that there is a correlation between the cycle, the day and night cycle, and the sun's northwest movement. And so it takes about 365 daily cycles of the sun to get this cycle. Two cycles are correlated. And one of them we call day and the other we call year. So how do we explain that?
If the earth is at the center,
Yeah.
the sun God may have decided to make the sun move from one place to another.
Yeah. But the assumption that the sun is stuck on the dome has to be changed because the stars are fixed on the dome. The sun is not. The sun has to do something else. Right? And also, mind you, the sun also has to revolve around the earth to get day and night. But in addition to the sun revolving around the earth, the sun has to do something else. Right? Now, here is a possibility. You have the earth, and you have the sun is going round and round the earth. But to get the other movement now, either you have to get the sun oscillate, right? In this fashion.
Oscillate and move.
Yeah, but in the classical view of things, oscillation is not allowed. Everything moves in a circle. Why? Because God is perfect. God created a perfect world. Circle and sphere are perfect. Therefore, everything God created circular movement. The natural movement is circular because it is perfect. This is a very powerful belief until Kepler came along. In fact, Kepler also had serious trouble in concluding that the Earth's orbit is elliptical, not circular. Initially, he thought there must be something wrong because he also subscribed to the perfect world theory created by God. Finally, he decided the data has to tell him which way to go, and he abandoned the circular movement theory and went to it. So what they did was to invent an epicycle. Epicycle is you move in a circular orbit, and then along with that you also move in epicycles. So you get the same effect, right? Cycle within cycle. So where the center will be along this, but then there will be cycles that will proceed. And you can show that you get the right calculations by adjusting the epicycle and its speed and so on. This was Ptolemy's explanation for the sun's yearly cycle.
A northward-southward shift.
Pardon me?
North-south shift.
Yeah, north-south shift.
And the movement, both of them were combined.
Yeah. The daily sun going from east to west is taking care of the sun's revolution around the earth, and the other one sun's epicycle. How do you do that here?
So which means epicycle essentially means that you are talking of the rotation. While revolution is taking place.
No, not rotation. Revolution again.
But revolution around what?
Around
A point.
So if you have a cycle, suppose this is the sun, and the sun is moving like this.
That is rotation.
Imagine that the sun center is here.
Huh.
Now do this.
That's revolution.
Right? So center is this trajectory. The center of the revolution is that trajectory. Around that you're doing this.
So spiraling around a kind of.
Yeah. That is one way of thinking about it. Yeah. Spiraling.
Say the moon.
Yeah.
around this.
Yes.
Maybe there are somewhere, maybe, I don't know, will that
that be something like 4 petals for this? Because that cycle is one motion here,
Yeah.
one oscillatory motion. So you
Yeah,
have
you
to
get
see,
the oscillatory motion effect by epicycle. Yeah.
so that epicycle, will it be 4 petals around rather than spiraling? Like, given that one away, one towards, and then to this side, and then to this side, what should be
The speed of
This
that
is,
second.
the speed will be lower.
You adjust the
Alpha
speed.
unit.
You adjust the speed such that you get this north-south shift
Yeah.
completely
Yeah.
in 36 years.
Yes, in
That's it.
365 days.
Sorry, 36.
In
What is
365
the
days.
day? 30 days, yes.
36 years is equal to 360.
Yeah, yes. Yeah. So that works. The question is, how do you get Copernicus to do it? Right? Ptolemy is okay. Of course, notice that Ptolemy's theory is going to be in trouble when it comes to Newton. But this argument was made prior to Newton, so it was okay for the sun to revolve around a point which didn't have any gravitational attraction.
Will people to come to this conclusion, this on their own, children? They,
No,
they-
epicycle is so strange, it's very difficult.
Supposing we ask two groups to, compulsorily prove the geocentric, will they be
I have
able to
not
do
done
that?
this in school. I have done this in
With
undergraduate classes,
And they could.
and they take some effort to understand epicycles. It's not easy.
They have to not, and they can't come up.
They can't come
No,
up.
no, no, they will not. I mean, even for those people, it was kind of very ingenious idea, because they need to get this done, get the movement right. So they invented the stuff. That's what scientists do anyway. They invent various kinds of things, including curved spaces, 7 dimensions, and all kinds of things. It's the same style. But you don't have to go to such lengths of imagination when it comes to the heliocentric theory. Rajesh.
No, I mean, so the epicycle model
Yeah,
explains the north-south shift
Yeah.
of the sun,
yeah.
and it also explains the revolution of the sun.
No, you have to say the sun revolves around the earth in order to get day and night, daily cycle.
Yes,
That's one.
yeah.
Now there's a yearly cycle. So you add epicycle to the original revolution cycle. There are 2 things now.
Hmm.
Right? Your theory is getting complicated. Right?
Yeah.
And the general idea is when you complicate theory, it's a bad idea. I mean, very complicated theories are bad theories and should be abandoned if there's a better theory, simpler theory. To get this effect from the heliocentric theory, what you do is you put the sun at the center, and here is the earth, and the earth revolves around the sun, rotates on axis. Rotation gives you day and night, but the rotation is at a tilted angle to the plane of revolution. I can't draw this properly, so I'm going to do something like this. Okay, this is the elliptical orbit. Imagine it this way, and the Earth's axial rotation is not like this. This is the plane of revolution. This is the Earth rotating. It's not like that, it's like that. So it is tilted to the plane of revolution. Do the pictures make sense?
Yes.
Okay. And this passes through the pole star. That gives you, remember, this was needed in order to get the nightly cycle of the stars, the whole dome. But there is no dome in the case of the heliocentric theory. Now when you do that tilt, notice if you look at the rays from the sun here, and let's say this is like that, and if it comes to the other side, the perpendicular ray here will be from here will be around here, and the perpendicular here will be around here. Shifts. Did I say that right?
No.
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 Okay. I wish I had a.
was the thing that was in the center?
This is the sun, and I'm going to draw this bigger, which will be misleading, and it's like this. And this is, let us say, this is the North Pole, okay? And this is the equator. Where will the perpendicular be when it is tilted like this? The perpendicular from
Yes.
sun rays will be somewhere here,
Yes.
right? Below the equator,
Yeah.
right? When you move this in here, this is the equator,
It will be above the equator.
it'll be above. So it is this thing that you see as the
Somewhere.
north-south movement of the sun. And it comes out of the axis, the tilt of the axis. So far, okay? This is actually much more elegant than Ptolemy's epicycle. This is easy to understand. I think with some drawing and maybe showing actual physical objects and so on, I think kids understand this. Yeah.
Leaving aside the fact that we know this is the truth, I have tried to be in the mindset that
Yeah.
the old one is right. And I find it difficult to accept now. This one. That
No,
one,
at this
the
point,
epicycle
at
also
this point,
seems
I have not
interesting.
given any arguments in favor of the heliocentric theory. They are equally good. We are not asking children to believe the heliocentric theory. We are simply developing both theories side by side. They are equal.
Okay.
There is no reason to believe the heliocentric theory so far. Notice that we haven't even come to Newton. Once you come to Newton, there are reasons for believing more reasons for believing. Reasons that we have not given so far. Newton will give some reasons, but let's do it pre-Newtonian astronomy. So we are not going to ask the children to believe us. Yeah.
This does not explain the pole star being fractionally, right?
Yeah.
If the Earth is moving around, the pole star is here.
Oh, that's not going to affect. Pole star is so far away that you don't get
angle
the.
of is
Yeah.
too narrow.
In fact, this was the argument that Aristotle made, that if the Earth were revolving, one should expect parallax error, and Aristotle argued there is no parallax error, therefore it couldn't be the case that the Earth is revolving. Right? And Aristotle's argument was perfectly rational. Had Aristotle concluded against the evidence that the Earth is revolving, he would have been irrational. It just happened that Aristotle didn't have telescopes. So he couldn't see parallax errors. Parallax effects. So once the telescopes were invented, we discovered that the expected parallax effects did exist actually. So had Aristotle been present at that time, he would have said, yeah, sorry, I was wrong, I didn't have access to that data.
What is parallax?
Oh, parallax is like this. If you are driving along a highway, so suppose I'm driving along a highway like this, and you have some trees here, and then you have the mountain, some far distant mountains. You will see, if you are moving, you assume that you are stationary, you will see the trees moving backwards.
But
But if you
mountains
look
are
at the
moving
mountain,
along.
the mountain seems to be going the other
Coming
direction,
along, yes.
right? That's parallax. And in other cases, if you look at the moon, this is my favorite example for little kids. There are three friends standing at night looking at the moon through the branches of some trees. And one child stays there, one child goes that way and sees the moon following him. Another child goes that way and sees the moon following in that direction. So three children have contradictory opinions, contradictory experiences. And the children come back and assert what they see, and they get into trouble. How you explain that? So this is a nice thing to throw at kids. How will you settle the conflicting perceptions, conflicting experiences? A little bit of optics will do it. Okay. So here is an explanation using the tilt of the Earth. The next phenomenon is using the summer and winter effect that we discussed to argue for tilt of the Earth. The same kind of explanation holds. There is the sun here, and there is the Earth here. And mind you, incidentally, most students think that summer and winter is due to the elliptical orbit. I've tried this here at IISA, and the first explanation that I get is summer and winter is because of the elliptical orbit, and they draw the ellipse like this. Very flattened. Actually, if you look at the actual case, it's the deviation from the circle is very little. Forget that one. And they say the Earth is here, and therefore it is winter. The Earth is here, therefore it is summer. So the idea here is, the closer the Earth to the summer, the hotter, and the far away, the colder. So it's a distance theory of summer and winter. Then you point out that according to this distance theory, you will predict 2 winters and 2 summers. And of course they recognize there's a problem, but it's easy for them to fix that problem. They say, okay, this is not where the sun is here, at one of the foci. So the incorrect prediction of 2 summers and 2 winters disappears. They're taken care of. So this is a good exercise in theory construction for the students. But then there is a then they will use exactly the same thing for day and night. Notice there is a daily cycle of temperature. It is hot. After sunrise, it keeps the heat keeps going up, and the heat keeps coming down, and again the next day it keeps going up again. And that is because you have the rotation of the Earth, and the sun is perpendicular to the Earth during noon, and at that point, in any place that is closest to the sun, that location is closest to the sun, hot, and when the Earth moves away, the distance increases. So the same distance theory will account for both summer and winter, the yearly cycle of temperature, and the daily cycle of temperature. Okay. Now, so as I said, the implicit assumption here is that the less the distance, the hotter the location. Then you point out that when you have mountains, you will then expect in the sun here, this is the mountain, top of the mountain is closer to the Earth, and the bottom is far away, so you should expect it to be hot here and cold here. That's not what happens.
It's because there is a snow on the top of the mountain.
And it's
Right.
because the winds are blowing very nicely on the top of the mountain, whereas they are stationary,
Yes.
relatively stationary
Yeah.
at the bottom.
There is snow on top of the mountain. That is,
That's
where
why
does the
it's
snow
cold.
come from? From the sun. I mean, absence of, yeah. Okay, but that's not this is a minor objection. The major objection will be that when it is summer in California, it is winter in Australia, and that comes from the heliocentric theory point of view. Notice that the perpendicular, imagine this as a patch of light, and when it is tilted like this, I should make it bigger, otherwise it's not clear. You have a patch of light, and you have the
Equate.
right. So it's distributed at this point. It's at a slanting way. Did I do this right? No, it's
Going
easier
in
to
the
do
southern
this.
hemisphere, it's correct.
First, let me do this. If you have perpendicular, the the light, the same patch of light is distributed, is concentrated in a certain area. But if you do this, notice that the area increases. So when it is slanting, the same energy is distributed over a greater area, so this will be colder, this will be hotter. And this is something that kids know from optics. You need optics to do many of these things. And the same thing happens because of the tilt of the Earth. Imagine, for example, that the Earth is kind of, I'm assuming the Earth is at this point flat. Okay, the Earth is like this, Earth is like this. All right, this will be cold. And when you move, no, this will not work if it is, I have to make it spherical. Remember that earlier we found that the perpendicular is here because of the tilt. And when you move to this side, the perpendicular is above the equator. So it will be summer here, and when it goes here, the winter on the other winter here. But when you move here, it will be summer here and winter here. So that explains why it's summer in Australia while it is winter in California. It's a tilt of the Earth effect, not the elliptical orbit. Yeah.
The tilt of the Earth stuff could also be explained by the Earth moving up and down, right? Rather than tilted.
If the Earth oscillates up and down, you'll get the same effect.
Same effect.
If the Sun oscillates up and down, the same effect.
Same effect, yeah.
But neither the heliocentrics nor the geocentrics wanted oscillation.
How about epicycles of the Earth?
Epicycles, well, let us say if Ptolemy didn't choose epicycle because he found it was complicated. But then that choice of not using epicycles was nice for Ptolemy when Newton came along.
Okay.
Because how do you revolve around something, a point that doesn't exist? I mean, point in the sense like, but there's no mass. So Newton will explain why things are not moving in a straight line, but moving in a circular elliptical orbit. That is something Ptolemy couldn't explain. So the combination of Copernicus and Newton gave you the right results.
Yeah.
Yeah.
An epicycle also won't explain why summer in California and winter.
You could, I haven't worked out the explanation.
You could possibly
But
create
Ptolemy had all kinds of complex explanations.
Yeah.
Epicycles of different kinds. So for example, he had epicycles for planetary motion. Very complicated epicycles. And that, okay. Let me go through that as well. I mentioned planetary retrograde motion of planets in the last session. And I have always found it difficult to help students understand that. And the phenomenon is like this. These are stars. Stars' relative positions are fixed, like the dome. Okay. If you look at a planet, then the relative positions seem to kind of move in relation to the stars in one direction, and after some time they kind of move back, and then they continue moving in the same direction. So if this is the main direction, this part is the retrograde motion. Right. So one interpretation is that the planets are indeed moving in strange ways. The other interpretation is that it's an illusion because of the movement of the Earth and the planets. So how do you explain this in terms of the heliocentric theory? Yeah.
One clarification. The retrograde is smaller than this.
Yeah.
So does it mean that overall they do keep moving in one side?
Yeah. It's a larger circle, whatever, etc. Retrograde happens only for a shorter time. So that is what needs to be explained. Why do planets move backwards? And the way I want to explain that, not really explain, but I once tried this in the classroom, and that seemed to work. I want to create a stick. Ruler will do equally well. So here is the sun, and here is the earth, and here is another planet, and here are the stars. Okay, so okay, let me see if this will work. Okay, so if you're here, this is where the planet is, and this is where we are, the Earth. Okay, this is the planet. And what you're going to see is, if you're looking at this planet, you will see the planet here. All right, you are here on the Earth. Suppose they have different speeds. Okay, I didn't draw these things right, so I'm just going to do the stuff without drawing the lines, because that will not help me do this. So here is the Earth, this is the Earth, here is the planet, and here are the stars. And look at the way the position of the planet, this is the position, observed position of the planet. This is the actual position, but against the stars. Okay. Suppose you are moving like this, right? Notice that it goes in this tip goes in this direction first, and then seems to reverse the direction when it comes round. Right? That is the retrograde motion. And when I do this on the board, students seem to understand what's going on. I have tried to show them various animations and so on. It's very hard for them to understand. And I haven't seen a good animation until he says there is a good animation. So you can circulate this. But I have been using this for the retrograde motion.
Why did you say that a planet was here but observed slightly away?
Because, okay, suppose this is the Earth, I am the Earth, and this is the planet, and okay, so I'm going to see, right, you against, so I'm going to see the planet near you, right?
Why?
Because it will be against this.
You don't know
Okay,
how
I'm
far
moving
it
it
is.
against you.
So,
But if I move, keeping this the same, but I'm now going to see the planet against Mother.
Behind,
Yeah. That's part of optics.
That
And I'm using this as a light ray. This is my light ray, and you will see the position against whatever is.
That part I understood about
Yeah.
the relative motions.
Yeah.
But why do you say that the planet was at a place X near you and you are seeing it at X plus something?
because you.
Oh, no, no, I
when you-
didn't, that's not what I meant.
When you're looking, you don't know how far the thing is. So
Yeah.
if I just put an object over here and assume there's nothing but that screen at the back, and you don't know the relative distances in this room, you were standing there. You won't know whether the object is here, whether it's a small
So
object
it could
there.
be closer also.
It could be a large object near you, or sorry, a small object near you, or a large object
Away.
You don't know.
Anywhere.
So you see it as a large object far away.
And if the background is fixed, then you see that object.
So you see it on the background.
You see it on the dome.
Yeah,
See it
the
on
dome is a reference point. The motion of the planets is seen with respect to the positions of stars, fixed stars. Another way of doing this in the classroom will be for one student for the observer to stand at the center and get two students to act as planets, one here and one here, and then ask the observer over there to look at the wall as the stars and see what happens when these two students go around. The observer at the center will see the planet. No, I'm sorry. Let me take it back.
Got it.
Yeah. I am the Earth. I am moving. I am a planet, right? And there is another planet here which is also moving in circle. And so this guy, the Earth, will see that planet against the wall, going this way first and then going backwards. But for that, you have to rig the students to, make the right kind of motion to see the effect. That will also sometimes work, but not always. Difficulty is that the Earth guy will understand it, but the remaining students will not understand it. So you have to get each student to do this.
To become the Earth.
That's painful. Yeah, and when they do it themselves, it's total chaos. There is no space in the classroom and so on, so I just gave up. There might be a better way of doing it, but I have not been able to come up with an appropriate
Slightly bigger bodies that actually move.
Yeah.
And each one gets a chance to sit there.
Yeah.
How
At
about
his own
doing
time.
it on camera? That person holds a camera, the earth guy.
Huh.
The earth guy holds the camera, that might be possible, yeah. I haven't tried.
Camera or light source?
Because there it will become, otherwise that
light
guy
source will
knows
not
from
be
his
able to see the
perception that okay, he's moving around.
It's not
He's
enough
just
to see
moving
the
around.
light moving. Or the shadow moving. Anyway, look, the idea is we can all experiment with this. If somebody comes up with the best solution, then we can circulate this. I am quite frustrated by this. It has been very hard. Okay, so that is the, yeah.
If you join the Earth, the other planet and the star, you get a line.
Yeah.
Okay, now if you imagine this and this moving at different speeds, I can sense that the inclination of this line will, the positive slope will change to negative slope at some point of time. I can see
Yes,
that.
for a mathematician it's very easy. But for students it is not easy. So this is what most animations do on YouTube. They draw a line and show that the line moves. But from that to get to the experience of seeing the planets going back and forth is not easy. Students don't see it. It's like a doctor sees the fracture on X-ray, but an ordinary person doesn't see the structure, see the fracture. So it's a problem in connecting optics to visual experience.
So you are superimposing an experience that you feel is happening.
Yeah, I think they have to get the reasoning and connect it to ordinary experience to understand it really. Otherwise they won't. At least in classes 7 and 8. Maybe after at a certain level when the abstractions can do it and they can do abstract algebra, that's sufficient. But not in class 7.
But they need to understand this by 5, 6, 7.
Pardon me?
Is this what is called an exposition?
What I am doing right now is an exposition. Because I am not getting you to do any activities, right? I don't think in some cases I might be able to do activities. For example, if it is day and night and doing heliocentric and geocentric, I can do the activity. But when it comes to planetary motion, it has to be exposition. They will not be able to invent this. This is very hard. Same thing with Foucault's pendulum. So there are areas where I have to give exposition. If they understand the reasoning, then I'm quite happy with that because my goal is part theory construction, but the majority of it, my goal is really not theory construction, but theory evaluation and the critical understanding of the heliocentric theory that follows from the critical evaluation. Those are the goals. The theory construction ability, maybe summer and winter, I have used that for theory construction ability. Yeah. Oh, I thought I saw a hand. Okay. The other one is Foucault's pendulum. That takes a little bit of imagination, but it is doable. Essentially, the point is that what I have done is to ask students to imagine a rotating restaurant, revolving restaurant, and you're standing here, and there's the pendulum swinging hanging on the ceiling. And if I'm doing this, what I'm going to see, and I do not realize that I'm rotating, then what I'm going to see is that the pendulum is rotating, or the swing of the pendulum is changing. That's what students get if you have this analogy. And Foucault's pendulum is something that Ptolemy will not be able to explain. Okay? No matter whatever he does in terms of epicycles and various other things, why should the pendulum on the Earth have this effect? You're not talking about the sky. It's motion on the Earth. There is no explanation other than Earth's rotation. So this was the first experimental evidence that astronomy produced. Until then, and even today, actually, astronomy is a non-experimental science. Now, students have this idea that unless you do experiments, you can't do science, which goes against the whole idea of astronomy, which is largely non-experimental observation. Apart from a few things here and there, it is non-experimental. So they have to be weaned away from this idea that unless you go to the lab to do experiments hands-on, there are no hands-on, you need eyes-on actually. You just keep
Minds
looking.
on.
Minds on, and even the eye actually is not of particular use unless you use your mind. And that is very important. So what I've been trying to do here is that minds-on part. Theory construction, theory evaluation, which is completely ignored in our education. Even by the people who are fairly active in educational reform, forget that science is not simply doing things with hands, science is doing things with the mind. And of course, a few things with hands-on also. Yeah.
So can such things be used if, let's say, if we have to teach a theoretical concept, let's say sometimes we find it very difficult in classroom to teach certain concepts from biology. So is it okay to use such an exposition method and speculative deductive reasoning?
In biology, you have to get them to construct theories which actually do not exist in the textbooks. So biology is a good place for getting students to construct theories. Physics is not. Physics may be for evaluation, but not for construction, because the theories in physics are fairly abstract and they are not easily constructible. Biology, on the other hand, is fairly easy. It's like linguistics. It's easy for the students to construct the theories. Relatively simple. But the theories do not exist. In physics, theories exist. If you open a physics textbook, you find laws all over, every page. Open a biology textbook, where are the laws? Mendel's laws, right? That's it. So you have to teach kids to construct laws in biology and connect these laws to construct a theory, which is not done in standard biology courses. And in fact, there is a huge debate on, can there be laws in biology? If you open Science or Nature journal, if you do a Google search on laws in biology, you will find people arguing in both directions. One camp that says there cannot be laws in biology. Biology doesn't lend itself to the laws, unlike physics. And another camp says, well, there are no laws in biology because biologists are not looking for laws. They don't have any training in looking for laws. Of course, how do you find laws when people don't look for laws? And I belong to that camp, the second camp. It's so easy to find laws in biology if you want to look for laws. And my belief comes from linguistics. There was a time linguists also said the same thing. Language is so amorphous and blah, blah, blah. You cannot predict anything, you cannot have laws. This was a situation in the 40s, 1940s. And in 1957, Chomsky came out with some extraordinary laws, and then everybody started looking for laws, and now it's full of laws. I mean, you can't do a linguistics course without having laws in every class. Except the word law is not used in linguistics. The word that linguists use is either rule or constraint, but it's the same thing as laws. Okay, what I am assuming that this is an exposition, and I'm hoping that this exposition can be done in various classrooms, that all of you will be able to do it, and occasionally with some activities as well. For this exposition is okay, yeah.
What age do you think this could be done within school?
I think not before 15, I'm guessing.
Yes,
So that means grade 9, 10, 11, 12.
Actually, one plan we had was to start with simple experiments like shadows in
Yeah.
class 5, and then each year build up a little such that the entire theory can be shown, say, in
Yeah.
9th grade. Built up gradually.
Constructing a theory of shadows actually is a good exercise in optics that will lead to this.
And then the summer, winter, and
Yeah.
then
Very slowly, exactly, yeah.
But we do it now, the concept.
I know. They teach Big Bang Theory in kindergarten. Yeah.
So either we not do it then.
If the school
Ideally-
allows you to do that,
Ideally.
if the school allows you to do that, yes, by all means. Don't tell them nonsensical things like the earth moves. Obviously, for them, the earth doesn't move.
Yeah, because telling them that and then questioning it 5 years later,
Yeah.
it kind of, I
Yeah.
don't know, it will probably lead to further confusion.
Though they think that this is simply reasoning for what they already know and they are bored.
Yeah.
Yeah. That will happen. They don't see the point of it. Why should I have arguments for what I already know, is the question. and they think some fancy esoteric stuff. But if you don't tell them that, and if they believe till class 9 that the earth is stationary, and then you invite them to consider the other possibility, they'll be shocked. That's the best time to do it.
I don't think that will ever
No?
happen. Because firstly, even by the 3rd grade, even if it's not in any book, all the
Yeah,
kids
they're going to hear from others. Yeah, that's true.
Encyclopedias,
Yeah.
people,
Yeah.
they know it all.
No, but at
And
least,
how? And
if
how
it is
do
not in
you,
the textbook,
Ah.
that is some help, I think. Because they don't have to write it in the examination note. Notice that beliefs get fossilized and hardened into stone when students are rewarded for those beliefs. So as long as students are not rewarded for their beliefs in the examination, they have some degree of
till the 8th grade,
possibility
anyways,
of
exams are limited, so
Yeah.
there aren't really exams. So that's not the problem.
Pardon me?
Till the 8th grade, exams are limited. The reward they're getting is their parents being happy with them when they're 5
No, the
years old.
teacher. Even though the public examination in the 8th grade, the teacher is going to test them. That will fossilize
No,
them.
but
Yeah.
I'm saying, bigger reward is when they're 5 years old and their parent comes says that, oh, my child knows that the earth is around.
Yeah.
Is there
Yeah,
a
yeah.
way of simplifying something and bringing it down to the lower classes and then building this up?
I think
Just
kids will
thinking
understand
aloud.
the daily cycles, that you can explain something using either the heliocentric
Both
theory or
geocentric
geocentric theory,
Yeah.
the daily cycle, nightly cycle and all that. Some of those things are easy. All you have to do is to bring an orange
Yes.
and a candle.
Huh.
And you can show that you can either rotate the orange or revolve the candle around the orange. Those things are okay. And ask them the question. If they know about heliocentric theory, ask them, why should you accept that? And create this
Yeah.
doubt in them to resist their parents. That may be a start.
And the next thing would be patterns of stars in the moon.
Yeah?
Next thing would be patterns of stars in the moon.
Yeah.
Waning and waxing.
Yeah. But to understand that stars are bigger than the moon is...
No, not that. The moon is waxing and waning.
Ha!
What's that?
That's right.
The cycle of that.
That is easy, yeah.
Yeah.
Moon's waxing and waning.
when you take the knowing a particular word as to be knowing the meaning of that word also,
Yeah.
and that is one thing that is being done consistently from grade 1 to
Yeah.
later, then it is very difficult to take them onto that. I have been doing this with a simple question that, and we can try it out here also, to prove that Earth is spherical.
Yeah.
We have been told
Yeah.
that Earth is spherical,
Yeah.
and I don't believe this. And I say that the Earth is flat, which I see. And the kind of arguments that teachers produce is not convincing.
What arguments do you use?
The
There are
same-
some nice arguments coming from Aristotle.
No, that the ship is coming and you can see the mast of the ship first.
That
and
is
then the-
Aristotle's argument, yeah.
Later,
Yeah.
there are 3 bamboos that are put up there, and the middle bamboo tall shaft is being put at 3 consecutive places, and the upper one will look higher, and the other 2 will be slanting like this. Same argument from the ship to the on
Yeah.
the ground, that you have 3 sticks put on the
On the ship, on
on
the
the
spherical.
on the ground.
spherical
Okay.
ground.
On the ground, and
Yeah.
then when you see that, you see the middle one slightly uppish, and these kind of things.
Which you really can't try out. You accept them.
No, but
No,
yeah,
no, even if you try out,
put it
and
this
even
way, minimally, we can say that if you have the opportunity, if you can look, you can see such and such data, and children may not be able to see that data.
No.
Or for example, data about eclipse and so on. So the argument in this case will be, people have noted such and such, and have argued for such and such. The grounds may not be experientially accessible, but that is also true about planetary motion, right?
yeah.
The retrograde motion is not accessible experientially for students, so all you can say is, people have observed this, and you have to trust them. This is like, the eyewitness testimony in a law court. We assume that the people who have made the observations are not telling lies. Now what conclusion will the lawyer make from those eyewitness testimonies? How did this disappear on its own? Battery.
Some retrograde motion is happening. Going forth and
Well, so what's the change of schedule today?
Well, we start presenting at 11.